All right. Welcome, everybody, to the 10th episode of the Blind Spot podcast. So, we feel like we're starting to get our sea legs, as they say with this. And we certainly hope that you're enjoying the conversations. We are certainly enjoying having these conversations, on pretty much life, the universe, and everything. These first 10 episodes, a lot of what we were doing was covering some of the topics from our book, The Blind Spot. But now as we move forward, we're imagining that we're going to start having some guests on and broadening the range of topics that we take on. I mean, we're always interested in science and philosophy and culture. But as time goes on, especially as we start to start having guests on, there's so many different aspects of this that we could talk about. The human future, the relationship between science and spirituality. So if you have suggestions for guests, please email us. We'd be happy to reach out to people. Everybody who comes on the show doesn't have to be like a famous scientist. We're looking just for the diversity of opinions to have these conversations. So thank you for joining us also on this 10th episode. So today it's just Marcelo and I, and the topic for today is quantum mechanics. We thought we'd do a little dive into our own understanding of quantum, what we think are the issues, and this question of interpretations. So Marcelo, let me start off by asking you, what was your reaction to quantum mechanics when you first learned it as a graduate or as an undergraduate?
Yeah, that's the question, right? Because as students, I remember I was almost angry because it was so completely contradictory, right? Because if you guys don't know, in physics, we learn the same thing 3 times, right? We start the first 2 years of university, we have classical physics, which is really mechanics, and then electromagnetism, and then quantum mechanics, and then statistical mechanics, right? And then the 2 next years, which are the junior and senior years, you do what? Classical mechanics, electromagnetism, quantum mechanics, and statistical mechanics at a higher level. And then when you go to grad school, the first 2 years, you do what? You do classical mechanics, you do electromagnetism, quantum and stats, plus a few extra courses. So you really redo these things. And the first encounter is always kind of like with quantum, is always, I think, a mix of awe and kind of despair, because it's so completely different, right, from the classical stuff that your intuitions are all thrown away.
Yeah, and I think first of all, I think that's just a great point you made about the fact that you have to learn these subjects 3 times over and over again. And like most people may not know. I mean, that's the interesting thing about, I don't know what other fields, what happens in anthropology but physics is really interesting that way, in that, right, you sort of climbing this ladder. And you learn it in freshman, each of these things. At a very basic level, you do very basic, simplified problems, which still, of course, are very hard. Yeah. But then there's the advanced undergraduate level, where you once again take classical mechanics, E&M, quantum mechanics. And as you say, that you get your first real introduction to statistical mechanics, thermodynamics, which is very beautiful. And then you do it again. So this idea that it's so complex and so layered that you kind of have you swim at the surface for the first 2 years, then you go down to the mid depths, in your final 2 years, and then grad school is this really deep dive where every problem takes, is 40 pages of algebra.
And the math gets more complicated by far as you move forward, right? And so does the concepts, because as you get deep, because in the beginning, it's sort of like, accept what we tell you, say the professors to the students. Yes, there is this thing called the uncertainty principle. Yes, there is this thing called superposition. But you don't have to worry about that. You learn it all later, right?
Yeah. Here's like the 2-line relationship, like the Heisenberg uncertainty principle. Delta position, change in position times change in momentum has to be greater than or equal to, the Planck's constant. And that's all they give you. Later on, you're going to derive that, right? Or you're going to, you'll see that by doing wave mechanics. But in the beginning, it's like, here's the relationship. Don't worry, let's just tell you what it means.
I think there is a bit of indignation that comes with, I've taught quantum mechanics. I don't know if you have or not, but I've done it for
I've never taught the
astronomy
courses and the astrophysics courses. So I've never
So it was always the same. And I did it at the graduate level and the undergraduate level and the very intro level, and you could see the eyes of the people, and there is this like how do I make sense of all this stuff, right? Because it's like, and the math is beautiful, the math is clear. I mean, the graduate level quantum mechanics course that I was teaching was based in this book by J.J. Sakurai.
Oh yeah, we use that too. Yeah, we use that book.
Which is just like it's all the math. Look, if you do this, if you accept these mathematical rules, it follows, quantum mechanics follows from that, which is like, wow, right? So that's like amazing. Of course, they don't tell you where the rules come from or why. There is a little bit of motivation when you talk about the Stern-Gerlach experiment, which was the first experiment that determined the spin, that the electron had a fractional spin. So the idea, people, is that, usually when you talk about classical physics, you talk about a ball spinning, right? You say, oh, the ball can spin at any speed, and it's doing that, and in any kind of like direction. It can do this, but it can also do this. It can rotate around its axis. So an electron, if you picture it wrongly as a ball, and that's the other thing that we do as you progress on this ladder of difficulty, all those kind of aids, intuitive aids that we use to help people visualize, oh, what's an electron? Well, think of it as a little ball going around an atom, like a nucleus, which is like the solar system model, right? So, and then you accept that and say, well, better not think of the electron. I think of it as a wire of charge around the nucleus. So I said, what? So it's not a ball anymore? And then you go, no, it's actually neither. It's really a probability wave that has some distribution, and then you really go ahead, Adam. You had something.
I was just going to say, because so maybe just let's step back for people to understand, like, why is quantum mechanics so shocking and why do we get angry? I think for most physicists, as we're kids, when we're first introduced to physics and we fall in love with it, we decide like this has got to be our lifetime passion. It's that promise of certainty, right? The idea that I learned from reading Carl Sagan or whatever when I was like, 11 years old was that with physics, with the laws of physics that Newton gave us, you could fire, I'm sorry for this analogy, but this is what I learned. You could fire a bullet and predict, and shooting at a deer, and you could predict exactly which hair the deer it would hit. That idea was true for every particle in the universe. You got absolute certainty. These mathematical equations, they gave you perfect knowledge of the future. And in this way, the term I read, the quote I read somewhere was, it was like thinking God's thoughts, right? That was classical mechanics. And the thing about classical physics, you start with Newton's laws, and then you progress to like these higher versions of it. So there was the Lagrangian mechanics, and then Hamiltonian mechanics, which were all basically still Newton, but they started getting very abstract and very, very beautiful. And so, we sort of came into physics thinking like physics gives me, a sort of perfectly objective, perfectly independent view of the universe, right? And that's what we come into it as 18-year-olds, right? And then what happens?
So that's the deterministic view that, the universe is like a big machine. And because it's a machine, you can crank it, and by cranking it, you know exactly what's going to happen next, right? So, and that works beautifully, for planets going around the sun and stuff like that, and balls rolling down planes, cars moving down a highway. But then what happened with the quantum revolution of the early 20th century, so the 30 years that shook the world, right? I mean, the first 3 decades of the 20th century, because all that certainty, all that view of confidence and objectivity and deterministic behavior goes down the drain. And not because anybody wanted that. That's the beautiful thing about quantum mechanics. It was a real drama. People hated it. People fought it back. So no, I don't want, even Planck, right? So Max Planck, who was the first guy in 1900 to actually come up with this notion that, perhaps the way atoms behave, the electrons can't be everywhere. They must have energies which are not continuous values, but only limited, possible values. But I have to explain this stuff classically, and he tried for a long time. He just couldn't, because he did ask for a different way of thinking about the world, which is awesome, but it was forced down by experiments, right? So that's the thing which is really cool about quantum physics. It's very different from relativity in a sense, Einstein's relativity. Yes, there were a few things that were not quite right with classical physics when we dealt with planets moving around the sun, like Mercury moving around the sun, that kind of called for some differences, but it wasn't as dramatic and radical as quantum. That basically said to people, look, guys, the way you're thinking about light and the way light interacts with atoms is just wrong. And you have to rethink the whole story.
That's a great point, really. I hadn't thought about that with relativity versus quantum mechanics. It's true, like, people with relativity were definitely, there was, everybody wanted there to be this luminiferous ether, which is what the medium that light propagated through. Everyone, people knew light was a wave, and light needs to, waves need to propagate through something. So there must be this thing called the luminiferous ether. And there were problems with it, but it wasn't like, I don't know, maybe, to me, my understanding of the history, it wasn't like everybody was like, this is the most important problem in physics. We can't make progress until we solve this. Whereas with quantum mechanics, it was really these experiments. The theory just was not matching at one after the other. Like everything with spectra, trying to understand why, if you take a box of hydrogen and pass an electric spark through it, it glows, but it only glows with certain colors. There's only like this wavelength and twice that wavelength and 6 times that wavelength or whatever, and no other colors. It wasn't a rainbow. It wasn't a continuous rainbow. And every element had that. And that was really, nobody knew how to make a model of that. And every model they tried using classical physics, continuous movement, things orbiting continuously around electrons orbiting continuously around a nucleus, just failed. And so it was these experiments that just forced people into this new view. And it's interesting if you look at starting with Planck all the way to, we're now celebrating the 100th anniversary of Heisenberg's famous paper where he comes up with the matrix mechanics of this whole other new mathematics that everybody was like, what the hell is that? It just got progressively more anti-realist, more anti, like, sort of that model in your head. So yeah, no, it's interesting. I like that point about relativity versus quantum mechanics was really forced on people by experiments.
Big time, right? And it started with light, light or electromagnetic radiation, really, to be more precise. Light just happens to be the kind of electromagnetic radiation that we can see with our eyes, but there's all these other kinds that we can't see with our eyes, but they're no less real, like infrared and ultraviolet, etc. And the simple calculation that guys wanted to do in the 1870s and do all these measurements about this were, okay, so imagine you have a box, right? And this box has walls made of a certain material. Let's say it's just made of iron, just for fun, okay? And then like an oven. And then you heat it up, right? And because you're heating it up, if you stick a thermometer, make a little hole in the box and you stick a thermometer inside, right? Well, there's going to be radiation in there because everything that has a non-zero absolute temperature has some level of electromagnetic radiation. It turns out that, for example, you guys watching this, you're all glowing in the infrared. You may not see that, but because you are at 98.6 Fahrenheit, hopefully, unless you're sick. But even if you're sick, you're glowing even brighter. But the thing is that you're all glowing, but we don't see that. But this radiation is everywhere. And so inside this box, there'll be some radiation as well. And when people calculated, okay, let me calculate the properties of this radiation, what is the frequencies that are allowed inside this box, and how much intensity it's going to have, the temperature of this radiation, because you can always measure. And when they applied classical physics to that, they got something which is beautiful. It's called the ultraviolet catastrophe, which is very dramatic, which basically meant that if you treated lights as waves, just like as plane waves, superimposing at every possible wavelength, then you'd have an infinite amount of radiation inside that box. That's what classical physics predicted. It was like, there isn't, because the box is not exploding. So clearly, and then people scratched their heads for 2 decades to figure this out, right? And that's where Planck said, well, maybe, what's going on here is that the atoms of this metal box are vibrating, they're emitting radiation inside, and only certain kinds of radiation fit in the box. And that's where the quantum idea comes in. The radiation is quantized, the energy of these waves is quantized. And he hated it, but he had the formulas, and he said, let me try this, see what happens. And it worked. So it was really to try to explain an experiment that quantum physics
was born. And then it just got worse, right? Because then it's this idea that like, oh, nature is not continuous, right? Like that the wavelengths, the energies that nature, that an atom will emit, they're not anything. You can't just say, oh, 14.2 nanometers, 14.1 nanometers. No, it doesn't work that way. There's only certain sort of, all of nature comes in packages and, certain discrete units of energy, momentum, etc. And so then once Planck got down that, started that, then it shows up again in, Einstein uses it for the photoelectric effect.
Yeah,
it shows that photons come in little packages. And then later on, Bohr says, no, actually, when electrons are orbiting, if you want to imagine an atom as being an electron orbiting a nucleus, like a little solar system, well, you know what? The orbits, there's only certain orbits. Like when you drop an electron into moving around a proton for a hydrogen atom, there's only certain places it can be, and it'll never be in between them. And it just gets more of this until finally, and I just wanted to get us to here so we can eventually get to the interpretations. By 1925 or so, quantum mechanics is complete in terms of its mathematical formalism, and that formalism is super weird compared to what came before. And so if you can give me a minute just to because what I really want people to understand, why exactly is quantum mechanics weird? Because I get this a lot. You've seen lots of things about Schrödinger's cat and, entanglement, but really from the physics point of view, why is it weird? So in quantum mechanics, once all the smoke had cleared by 1925, 1927, their way of understanding quantum mechanics, there are two pieces. There's two equations that are fundamental to this. And they're actually not that hard, as equations go. The first one is what's called the dynamical equation. It's the equation that tells us if I have an electron, how is that electron going to move around? And it's called Schrödinger's equation. And dynamical equations, physicists have lots of these. We love our dynamical equations, right? There's Newton's equations for, matter bouncing around. There's the Maxwell's equations for electromagnetic fields, right? We have lots of dynamical equations. Those are the things that we think of as being the mind of God, right? They're these beautiful equations. They make predictions. Everything's wonderful. Now, we can talk about how Schrödinger's equation is different in a second, because it's not predicting where the electron is. But so we have a dynamical equation. Old story, physics loves, we love our dynamical equations. But that wasn't the only part. Also, what came along with the dynamical equation, with Schrödinger's equation, was what's called the Born rule. And the Born rule said, hey, guess what? That thing, the dynamical equation, that thing that predicts where, is going to tell you where the electron is, actually, it's not a prediction anymore. At least it's not certainty. The Born rule told you what to do, how to take the results of the Schrödinger equation and turn them into probabilities such that you would only know where the electron was going to be after you looked at it. So basically, the Born rule says you've got to look at it, right? The Born rule tells you when you look at an experimental setup, at an electron in a box, the Born rule tells you sort of how to assign probabilities from the Schrödinger equation, and that it's not until you actually look that the Born rule will kick in. So in other words, the Schrödinger equation works fine if you're not looking for it. But the moment you look, you've got to stop using the Schrödinger equation and switch over to the Born rule to determine the probabilities of your result. And that is really where the true, to me, I don't know, Marcelo, the true freak out comes from, is that suddenly the observer steps in, the measurer, and now suddenly you have to take into account that, you're making a measurement. Stop using that dynamical equation and now use this Born rule.
Yeah, I would like to even preface this by saying the following, that the weirdness begins with the structure of the equation itself, because in classical physics, right?
Which equation? The Schrödinger equation?
Well, yeah, the Schrödinger equation, or even worse with the Heisenberg equation, because in classical physics, when you write an equation down, it's usually something like, I have a little particle, it's moving around in space. What is its position as time goes by? What is momentum? So the equation is describing something that you immediately identify as part of reality, the position of a particle in space. Everything has a position. You are sitting down watching this, you have a position in space. The equation that would describe you would say, he is in this position in space. So the equations are about things which are concrete. When you go to quantum mechanics, the equation that tells you what's going on with the electron is not an equation that tells you this is the position of the electron as a function of time anymore. It's an equation about things that don't really exist in reality. It's an equation about probabilities. And that's just very different from classical physics, right? So everything becomes, and I have to say, Schrödinger himself, the guy who invented this equation, I think in 1926, he hated the fact that the equation was not a true wave, like, oh, it's a wave, it's a wave equation. Oh, what's waving? Oh, the electron is wave. No, the equation does not describe a wave like a water wave or a sound wave, anything like that. It describes a wave of probability, which is really awesome and strange. And it's not even the wave of probability, because the equation, to get to the probability, you have to get the stuff that is in the equation, which is called the wave function. And you have to take what we in math call the absolute square value of it, because it's not a real number, it's an imaginary.
Got an imaginary. That's the wild thing about the Schrödinger equation. It's got an imaginary number in it. It's got so the result comes out with that class of numbers that don't really exist, the square root of 1, right? So yeah, right there it tells you that this is not an equation that is telling you about reality. You got to do something else to get the thing that connects to reality, and that is taking the absolute value of it, which is. And that's where the Born rule comes from. The Born rule tells you.
That's where the Born was the guy who figured it out, right? Because everybody was like, what the heck is this equation telling us? Schrödinger first said, well, it's just the electric charge of the electron that is distributed in space, and that's what's waving. So he had this idea. And it was Born that said, sorry, folks, this is not an equation about anything that exists in the world. It's about the probabilities that you have to calculate in order to find where your measurement is going to determine
your measurement, right? Because it's now and there's a certain way of looking at this that now nothing, the electron doesn't have a position until you look at it, right? And so this has been the struggle. So let's just unpack this a little bit more. So, okay, so there's this thing called the Schrödinger equation. The Schrödinger equation is not a description of space and time the way we're used to with Newton's equation. The solution, when you solve Schrödinger equation, so let's just do terminology here. You're going to get what we call the wave function, right? And the wave function, because Schrödinger's equation is an equation for waves, the wave function's got this really interesting thing about the way it's built, is that it's going to have a bunch of pieces. So imagine I've got an electron in a box with a partition, and the electron's going back and forth, between the two sides. Now, the electron can either be in side 1 or side 2. Right? In classical mechanics, you'd have an equation, if you're sure your Newton's equation would produce a solution, which would tell you it's definitely in 1 or it's definitely in 2. In quantum mechanics, the wave function, the solution to the Schrödinger equation says, well, there's a solution for it being in 1 in the first side, and there's also a solution for it being on the other side, and they get added together. That's what we call, very important term here, superposition. The wave equation produces the wave function. The wave function has 2 parts for this case. One where the particles in side 1, one where it's in side 2 at the same time, right? And so that's really weird. Before anybody looks at the box, right? So this is obviously, we're heading towards Schrödinger's cat. The electron is both on the side 1 and side 2. They are what is called superposed, which is makes no sense from a classical point of view, right? You're like, no, look, it's either inside 1 or it's inside 2. It can't be in both at the same time. But the solution to the Schrödinger equation says, yeah, sure it is. And then that's why you need the Born rule. The Born rule is what assigns probability and tells you, well, when you really look, you're going to see, there's going to be an 80% probability that you'll see it on the other side. But the weird idea is that, like, before you look, before you do the experiment, quantum mechanics gives you no way of saying that it's in one side or the other. It's in this weird state of it's not on one side, it's not on the other side, it's neither not in one side. And you got to run through the whole logical things. It's this whole other kind of class of description that really nobody knows what to do with.
And that's where the fun starts, right? Because then you say,
that's
well,
where the fun starts.
Right? Okay, what do you do with this, right? I mean, of course, and people know this, like, if you don't even think about it and you just calculate, which is the famous shut up and calculate approach, quantum mechanics is the most precise of all theories of physics. We can calculate properties of the electron to 12 orders of magnitude, which is like unprecedented. You cannot do that with anything else, right? So the theory works beautifully, right? But then you start to say, but wait a second. What if you start thinking beyond the theory a little, beyond the results, and you say, what does it all mean? What does it all mean? And you go, can something be in two places at once? Is this really happening in nature? Or is it just an artifact of the calculation, of the mathematics that and then you start to say, well, what is reality, right? I mean, is an electron in a reality where it can be in many places at once, or it can only be in one place, and we're just getting very confused. And then, so what quantum mechanics is doing is sort of like moving that certainty that classical physics says, yep, we know what reality is. We have little balls moving around, pushed by little forces, or we have fields of electromagnetic waves that propagate in space at the speed of light. That's all wonderful. And then you go say, but wait, now I don't even know where stuff is anymore, right? And even worse, apparently you can only know where stuff is when you interact with it. And then the question then becomes, but wait, if that's true, does that mean that in order for reality to exist, you have to exist? Because you have to interact with the electron before we can say the electron exists? So some of these guys, in the 20s would say, nothing exists until we interact, like Jordan and some other guys, which was one of the big dudes, say nothing exists until we interact with it. And then you go, wow, does that mean that reality is made up of our minds, that only through mind reality exists? And that's where the spiral of Lala goes into quantum mechanics that we should also talk about.
Yeah, the sort of new age stuff. So what's interesting is that, right, so the first generation, the founders of quantum mechanics, Bohr and Jordan and Pauli, they were, a lot of them were very philosophically well trained and were really, so I mean, we have to contrast Einstein's view, say, from Bohr. But so what became the so-called Copenhagen view, which was Copenhagen was where Bohr was. And of course, there was not one Copenhagen view, but this view got associated with Copenhagen. These guys were very interested in philosophy, and they were really willing to push on this idea of, like, nothing is there until we interact with it. It's as what I forgot, I'm not sure who said it, but it was like, what we now have is that quantum mechanics is not a theory of the world itself, it's a theory of our interaction with the world, right? Somebody said something along those lines.
Perfect, yeah.
So they were really willing to sort of see quantum mechanics as sort of leading to a whole different way away from this perfect certainty that, was classical. But then World War II happens, and the center of quantum mechanics moves from Europe to America. Right? Because all the physicists, fleeing Nazi persecution, came to America. And then you get this sort of, I think this is very interesting, you get this very kind of American hard-headedness. It's like, I don't really care about, this philosophical stuff. I just want to build things. And so, Feynman was kind of famously not interested. But then you get people like DeWitt and Everett, or Everett in particular, right? So Everett was a physicist in the 50s who worked with John Wheeler, who wrote a thesis that propounded what would become what we now know of as the many worlds interpretation. And what he wanted was to return physics to that perfect view, that it gave us a perfect view. So from that perspective, from what Everett came out with, was that all of those possibilities that are in the wave function we talked about, the electron could be in box one or on side one or side two, or if it's a huge box, it could be, in 15 different places. Everett was like, oh, it's in all those different places, but in different universes. And when you make an observation, what happens is the universe splits into there's one version where you're looking and seeing the electron in side one, but there's another version of the universe that just split off into a parallel reality where, there's another you that sees the electron in side two. So it's interesting that, the first generation wanted, of quantum mechanics, the founders were willing to explore this idea that somehow there's this interaction between us and the world that matters. And then sort of as time goes on, there's a pushback against that. And like, no, reality is reality. Physics gives us the absolute rules of reality, independent of us. Stop talking about, observers affecting the observed.
Excellent, because that is just to connect with what we were saying before, to show how Everett is the exact example of someone that did not accept the fact that equation, the wave equation of quantum mechanics, is saying something which is not directly related to reality. You say, no, that wave function there, that thing is directly related to reality, right? It just so happens that it's a reality that is not accessible to us, because every time you make a measurement, you have this split of probabilities. So different things happen in different universes, but he's willing to pay that price to keep the sanctity of the mathematics, so to speak. Like this equation cannot be telling us something which is just a tool for us to understand reality. It has to be telling us about reality. And if it's telling us about reality, it's telling us that every time there is a measurement, reality splits into parallel universes. So you happen to see one aspect of reality, but all these other ones. So to me, that's just mind-boggling, because it's showing how far away you want to go, right? In order to justify
the price you have to pay, right? The thing is about quantum mechanics is that so now we're sort of, hopefully you have a little bit of a handle on what the weirdness of quantum mechanics is, right? Schrodinger's equation, the solution to it is the wave function. The wave function has multiple parts, that are superposed, that are all real at the same time. And then there's the Born rule, which sort of relies on you looking at it in order to select out which of those realities are true. In order to interpret, you can either choose not to interpret, say, hey, look, I just want to build a quantum toaster, as one of my friend professors here says. But if you want to say, like, yeah, but what is it telling me about reality? Every interpretation, and I think that's what we'll do for the next 20 minutes, we'll talk about these different interpretations. There's a price to pay. You're never getting that beautiful Newtonian God's eye view back. That's over. It's done.
And, it's important to always remind people that we are talking about the physics of things which are really, really tiny, So when talk about quantum mechanics, you're not like talking about us or big things, right? We're talking about very tiny things which are way beyond our perception, right? So you don't see electrons directly, right? You don't see, of course, there are experiments where you can see amazing things that electrons do. So it's beyond our sensorial apparatus. And that's what makes it a little more complicated, because about this invisible world we don't see, we only see it indirectly. And because measurement, that's why I want to go, that's where I'm going. So, because, because you don't see an electron, how do you even know what you're talking about when you talk about experiments? Well, the signal that this electron has when it hits another electron, for example, that thing has to be amplified, right? And this amplification is a cascade of amplifications, because, an electron is so tiny that you don't, in order to get an observation of an electron, what's an observation for us? Well, it's a flashing light, it's a blimp of an alarm, is something you can see, is a stain on a piece of paper. Electrons don't do that. So you need to amplify all of this. And that is where the confusion begins, right? Because in order to see something or hear something, you are talking about a classical world. So in order to reveal the physics of the quantum world, you're doing experiments that by necessity amplify, and by amplifying change the quantum behavior, at its core.
I think that's a really important point, that, right, that, the reason we're led to these like weird conceptions, these things that confronted with the idea of like, does the observer participant, affect reality, is not because we see it directly, but we have apparatus. I've got a big, machine with a bunch of dials on it, and I set up an experiment, and the dials read 5 rather than 4. And so because of that, I now have to build a theory, and my theory then has these strange aspects of it, where now I have to ask about superposed possibilities, dead cats and live cats, the box particle being in side 1 or side 2. And so, yeah, it's never a direct apprehension. We got so good at building apparatus to probe smaller and smaller time scales and size scales that we were enlarging our sensorium in some sense, but mediated by the apparatus. And that is what forced us to really reconsider what we thought about reality, but it wasn't a direct, the world up here. And then we talk about our intuitions. The world up here, when I look at if I look away from my coffee cup, I still think it's blue. And I look back, oh, it's blue, right? But now with the electron, it's like, well, no, if we use the color analogy, the electron is neither blue nor red until you look at it. And if you look away again, it kind of will evolve back into a superimposed state of red and blue. And, it's not until you come back and look at it that it becomes red or blue, using that analogy. So, yeah, it was really this mediation by apparatus that sort of forced us to reconsider what we think is, do things have properties before we interact with them?
Yeah. And honestly, I don't know if there is a clear answer to that. I think, right? I mean, there are properties that we measure, the electric charge of an electron, the mass, we know how it's spinning around. We find out it can only spin in 2 different ways. So it's not like a normal ball at all, right? And you can measure all that very well, but you measure not one. Usually, now you can actually measure single electrons, but in the past, you had to measure many, many, many and do a statistical analysis of what's going on. So when you say, well, the probability of the electron being here at this point is 30%, but you can only say that if you do 1,000 experiments, and 30% of the time, 3 out of 10 of these electrons will actually be here. Otherwise, so that's what you mean by having a statistical theory of nature, right, of the behavior of little things.
But it's important to understand that the probabilities, and this is important, like, statistical mechanics, which talks about, I've got a box full of 10,000 particles, I can't follow every one of them. With a modern computer, probably could. But let's say I have Avogadro's number of particles. Statistical mechanics works with probabilities, but their probabilities based on our not having all the knowledge we need. It's a way of dealing with the overwhelming number of particles. In quantum mechanics, the probabilities they're part of the problem. Like, they are built into nature. These are not. And that's where it comes back to us. As great physicist James said, it's not nature's probability distribution, it's yours. Their probability distributions don't exist out there in the world. It's always your probability distribution. It's a measure of your knowledge of the world. And so that's why some people, at least, and probably Marcelo and I are sort of on this, what's called quantum Bayesianism, about thinking about those probabilities. Those are telling us, the fact that their probabilities are built into quantum mechanics is telling us that we're built into quantum mechanics. That God's eye view that Everett was trying to return to is just simply, it's not going to work. But again, there's a lot of debate about this. Marcelo, just one thing I wanted to bring on, if we're doing the history, right? So Everett in the 50s proposes this, trying to get back to objective reality. And then what happens is, by the early 70s, late 60s, the hippies who saved physics, right? This is an important part of the story. These dudes in California, Berkeley, sort of started to resurrect, sort of asking questions, the philosophical questions about quantum mechanics. Like, everybody, people just didn't care. Everett hadn't made a big impression. And it was a bunch of these guys working in quantum optics, which, by the way, started at the University of Rochester. Thank you very much.
Yeah.
Really started asking those questions again. And out of that comes eventually quantum information theory, which is the basis of quantum computing. So I think that's an interesting. I think one of your students did this. Is that true?
Yeah, David Kaiser, who was my student actually at Dartmouth. He a senior honors thesis student. Now he's a professor at MIT. He wrote this awesome book, How the Hippies Saved Physics, right? Which is the history of exactly this moment where all this philosophical, let's say, discontent emerges, and people say there has to be something else. There has to be something a little deeper about what's going on here. It can't just be calculations, and then slowly but surely, what was then unthinkable, which is to deal with the interpretation of quantum mechanics in the 50s and 40s, becomes more and more kind of like in vogue. And I would say that now, in the 21st century, there are lots of very smart people worrying about this, with many different candidates for what is your favorite version of the interpretation of quantum mechanics, right? And it's funny that we can use a theory so well and we don't know what it's telling us, deep down about the nature of reality.
Let's talk a little about the hippies, though, because that was an important. What's interesting about, because that was the beginning of quantum woo, as we like to call it.
That's true.
Right. So these guys, it's California. It's 1973. Everybody's smoking huge amounts of weed, or doing other things.
Yeah.
Right? And there's a bunch of bright young physicists who are wanting to ask the questions about, like, what does this mean? What is the wave function? What is a superposition? How can a particle be in two places at once? And what's interesting about this is you see sort of it goes off in two directions. There's one group that really is going to stick with the physics and is going to start probing what measurement means, and developing a mathematics that is appropriate to trying to think deeper about measurement. But then another group is kind of going to become science popularizers. And they're going to write books like The Tao of Physics by Fritjof Capra. Or there's another guy whose name I can't remember. And it gets tied.
Gary Zukov, right? The Dancing Woolly Masters.
Dancing Woolly Masters. He was a journalist, though. There's another guy whose name I can't remember who really did a lot of popular, like picture books, and I can't remember his name. He called himself like Captain Quantum. He was like sort of at the far edges of this identification of quantum mechanics with New Age thinking. And it was, so the Tao of Physics is interesting because I read that when I was a freshman at the University of Colorado at Boulder.
So did I when I was a freshman in physics.
Yeah, and it blew. First of all, it was a very nice description of quantum mechanics. His descriptions of
Capra is a very smart guy.
Very smart guy, but he then links it to Buddhism. He says, "Oh, this shows how quantum mechanics recovers Buddhist philosophy." And there was a huge problem with that, which we can talk about in a second. But the important thing for the moment is that those books, and then the Dancing Woolly Masters, which was Gary Zukov's book, which was those books were hugely popular. And this idea that like quantum mechanics shows us that like, our thoughts control the world. We make the world with our thoughts. And then, oh God, who's the guy? Quantum healing. The famous. Who am I thinking of?
Quantum healing. Then you start going like into crazy stuff.
But who was the guy who
there's a guy called Goswami who wrote
I'm thinking of the one who's even more popular. I can't remember his name. Indian American, I believe. Deepak Chopra. Right?
So he used some of these concepts in quantum to kind of legitimize or give credibility
to New Age,
some half-baked ideas in New Age, like quantum healing and quantum whatever, and that superpositions happen between brains, and that
it just went on.
Has to do with all sorts of stuff like that, like entanglement and all those woo words, right? That we use in quantum.
So if you type in quantum, go to just the internet and type in quantum love, quantum loving. I mean, it's amazing. You'll find so many, like the word quantum just gets put in front of all of this New Age stuff. And that's as bad as the worst, I mean, I think we both have pushed back hard on that. It's relatively innocuous, but it is, people have this idea that quantum mechanics, sort of tells us that Buddhism is true, which as a Buddhist, I push back on that, because the problem with the Dancing Woolly Masters is he got the quantum mechanics right on a certain level. Well, first of all, he said the problem with the Dancing Woolly Masters, he was only looking at one interpretation of quantum mechanics, right? He was taking the Copenhagen inversion. Never mentions Everett or anything else. Maybe, I don't know if he never mentioned it, but he has only one version of quantum mechanics and its interpretation, and only one version of Buddhism, right? His author is not taking into account the fact that, like, there's a lot of different Buddhisms.
But the Capra book, I was the one thing that blew me away is when in the Capra book there is a picture of the yin and yang, the Taoist. It wasn't just about Buddhism. There was a lot of Taoism in there, right? And that was Bohr's when Niels Bohr was knighted by the Danish crown. He chose a coat of arms, and his was the yin and yang. And it said, contraria sunt complementa, which means, opposites complement each other, which was about the wave-particle duality, right? That an electron is not a wave, it's not a particle. These are just metaphors that we use to try to describe what we can't really put our hands on. But once you measure it, it can be a wave or a particle. So there's this, so it's both and it's one. And so this oneness, and Capra goes way out with this idea, this oneness in reality. And I have to say, for my 18-year-old mind, that was really amazing.
It changed my life. It's only looking back on it that I'm like, but it was that book really, I can remember being in the library reading it, being like, whoa. And then, I had to go into class and I was taking modern physics, which was like that simple introduction to classical or to quantum mechanics, and just being like, wow, like
That's not really what quantum is about, right?
No.
It's really about describing those little particles. And the interpretations, we didn't even talk about cubism.
Why don't we leave that? Yeah, what I was going to say is, because we're almost at 15 minutes. So why don't we say, so this episode, this was a super fun conversation just about what quantum mechanics is. We didn't really dive into results hugely, but we could save it for another time to actually go deeper into the interpretations. Because there's probably like at least 4 or 5 interpretations that we would like to unpack. What do you do with superpositions in the wave function? And what do you do with the Born rule? And so, we could spend some time next time or another meeting talking about that.
Yeah. And we didn't really talk also about the Nobel Prize winners that measured all the entanglement and, the whole spooky action at a distance and why that's so incredible. So it's endless. You can talk about quantum mechanics forever. It's just so much stuff.
Well, we will. So why don't we just say, okay, everybody listening, we will have more quantum mechanics episodes. Maybe we'll have some guests on who are working at the forefront. We might have Chris Fuchs on, who's the founder of Cubism. There's some philosophers we could have on to talk about, the different ways of looking at quantum mechanics and the issues it raises. So let's set that intention. We're going to set our intention like we do in meditation for future episodes on this.
Fabulous. All right, my friend. So everyone, thank you. And we'll see you very soon.
Bye.
Bye.